Hey, Thomas, are we all ready? He gives us the thumbs up. All right, let's begin. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. It is my pleasure to be your host tonight. I am Dr. Frank Summers of the Space Telescope Science Institute Office of Public Outreach. When you came in, I'm sorry I didn't put any pictures over this side. Over that side, there's a plenty of pictures. Tonight's pictures are not the same. There's a whole jumble of pictures. We have a bunch of OPPO staff moving offices, and when they move their offices, they say, where did these come from? And then they go, here, Frank, give these away at the public lecture series. So tonight you have a whole bunch of cool images and random lithographs that have come out of people's offices. If you didn't get one on the way in, please pick one on the way out. What do I have here? It looks like this is a wonderful edge-on galaxy, NGC 5866. All right, if you want 5866, hurry down here afterwards. It'll be right here. All right. Tonight's talk will be the Cosmology Large Angular Scale Surveyor, which in the tradition of physics and astronomy has a nice acronym of CLASS, okay? So you're going to get a classy talk tonight, okay? Really classy. All right, and next month we have Christine Chen talking about debris disks and the evolution of planetary systems. January, I don't have a speaker for January. It's difficult to rope somebody in for January. I will work very hard at it over the next month and announce that. So right now we still have our infamous TBA. And in February we have a very special talk. Priyamvada Nayarajan from Yale is coming down, and she will be giving a talk on her book, Mapping the Heavens, okay? So it's rare that I get because I have no travel budget for this lecture series, okay? So when I can get somebody in from outside, I'm really happy to be able to bring you somebody who's not from Space Telescope or Hopkins. Nothing against the Hopkins and Space Telescope people, because we are wonderful folks. But being able to bring you somebody from another university is also pleasant. Okay, I'll talk about construction. Since you're here, you know about the construction, but for the people watching this on the web, if you come to visit us, the road north of us is closed. So you can see the map here. This red stuff up here is closed. If you try to come in here, you won't be able to. You have to come all the way around here and then back up to get to us, all right? If you want to know more about this here, the website is here. There's the website on the San Martin project. This will probably last through next month and will not be there in January, we hope. We don't know. We'll let you know next month what the condition is, okay? All right. Let's see, our website, if you just search for Hubble Public Talks, you should find this. It has our list of our upcoming lectures. It has links to our online YouTube and webcasting, and as well as the archives, our playlists on YouTube and our archive from our wonderful webcasting folks. There are 10 years of these wonderful public lectures there for you to peruse. All right, you can also sign up for our email list, which will be helpful in December when we send out the email saying, yes, it's open, no, it's not open, for the construction update, okay? We can also, these announcements can also be signed up at maillist.stsci.edu if you should so desire. It's just much easier from our website. If you would like to send us mail and have us a comment or question, it's publiclecture@stsci.edu. We're also on social media, Facebook, Twitter, Google+, Pinterest. I'm on Facebook and Google+ and Twitter, and I have a blog on Hubble site if you want to follow some of the things I like to talk about. All right? There will be no observatory tonight. One, it's cloudy, and two, we have a special treat for you tonight. Our speaker has invited you across the street to look at the observatory that he's building, the facility for the Cosmology Large Angular Scale Surveyor. So at the end of the lecture, if you would like to go across the street to the facility, hang around, and after Toby's finished answering his questions and put away his laptop, we'll take you across the street for that, okay? All right. Now, our news from the universe for November 2016. Our top story tonight, make the universe great again. You knew I couldn't get through this without one election pun in this, right? Okay, so what am I talking about? Well, let's start back in 2004 with the Hubble Ultra Deep Field. Now, this is a picture of lots and lots of galaxies. How many galaxies? Well, some of you may know, but actually we do a educational activity where middle schoolers count all the galaxies in the Hubble Ultra Deep Field. How do we do it? Well, we divide it into 100 smaller squares, okay? And then we have the middle schoolers look at these individual squares and then count the galaxies in them, okay? They usually come up with like 50 or 70 galaxies in these. And then if there are 100 squares and there's, say, 50 galaxies in each, how many are there total? 50 times 100, 5,000, okay? So they tend to get 5,000, 10,000 galaxies or so in this. And well, 5,000 to 7,000 is what the middle schoolers usually estimate. When you do it really carefully by astronomers, they count about 10,000 galaxies in this image. Now, this is a really tiny image. So if there are 10,000 galaxies in this image, how many are there in the entire universe? Well, to do that, you then have to know how big this is on the sky. And so we walk the middle schoolers through that part as well, and we say that, okay, well, here is the size of that ultra deep field compared to the full moon, the size of the full moon on the sky. All right? And it's, you know, it's a small part of the full moon. And the full moon itself is also a small part of the sky. And if you do the mathematics, all right, the size of the Hubble Deep Field compared to an entire sphere, the number is, across the entire sky, there are 12,746,784 patches the same size as the Hubble Ultra Deep Field. Okay? So, 10,000 galaxies in the Hubble Ultra Deep Field, 12 million ultra deep fields across the sky. If it's representative, then we get about 120 billion galaxies across the entire sky. So using that ultra deep field, which I said we observed over a decade ago, to the depth of the ultra deep field, there are roughly 100 billion galaxies in the universe, okay? And that has been sort of our standard number for the number of galaxies in the universe for over a decade. But what about the galaxies that Hubble doesn't see? Because notice, this says to the depth of the Hubble Ultra Deep Field. There are things that Hubble doesn't see, right? They could be too faint for Hubble to see them, or they could be too small for Hubble to see them, or they could radiate in infrared or other wavelengths that Hubble doesn't see, right? So, we recently had a paper called The Evolution of the Galaxy Number Density at Z less than 8 and Its Implications, which may not make much sense to you, but the idea is to try and account for all the galaxies that we don't see in the Hubble Ultra Deep Field. So, here is the study. And I'm going to read this verbatim because there's a lot to it, and I'll think. How many galaxies are potentially detectable within the universe if deep imaging over all wavelengths could be carried out in every location of the sky without any interference from the galaxy or other contamination? So that covers all the things that I just said. The entire sky in all wavelengths without any of this foreground contamination or stuff blocking, right? Which you could see every single galaxy out there. That's what this study is trying to do, okay? What is a galaxy for them? They say, well, they consider galaxies down to 1 million solar masses. Our Milky Way galaxy total mass is about 10 to the 12 solar masses, maybe 10 to the 11 solar masses in stars. They're considering things much, 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 much smaller, okay? Even the Large Magellanic Cloud is like 1 billion solar masses. So this is 1/1000th of even, you know, our satellite galaxies. So these are really down, they're trying to look at the very smallest type stuff for galaxies. And also, they're looking at the number per co-moving volume. I need to point this out because we're going to talk about number density. And we know the universe is expanding. And so as the universe gets bigger, of course, you have fewer galaxies per volume, right? No. Not in this. We're talking about what we call co-moving volume, so the expansion of the universe is already factored out, okay? So the densities are factored, the expansion of the universe has been factored out when we're talking about the densities here, okay? So this is one of the key figures in their paper, all right? And this on the y-axis is the number density of galaxies, all right? And on the x-axis is time in billions of years. All right, starting at the Big Bang here up to almost the present day over here. And there's lots and lots of points because they're trying to normalize it to data that is observed. Galaxy surveys looking deeply at the various galaxies in the universe, counting up galaxies, and they're trying to normalize their theoretical prediction to that. And this solid line is their best fit to the model results. And you'll note that it's down around 0.1 for most of its length. And then in the first billion years of the universe, it jumps up by a factor of 10 or more. Okay? The number of galaxies per unit volume in the first billion years is much, much larger than what we see out here. And where are we going to see most of our galaxies with Hubble? Well, we're going to see them mostly out here. That first billion years of the universe is extremely difficult to look at. Okay? So they're saying that we're missing a lot of galaxies over here because the number density is so high and we're not seeing them. They say that there are more low-mass galaxies per massive galaxy at high redshifts than in the local universe by a large factor, a factor of 10 or so. And their result is the total number of galaxies in the universe is 2 trillion, almost a factor of 10 higher than would be seen in an all-sky survey at HUDF depth. So if we could do the Hubble ultra-deep field across the entire night sky, they're still saying we would only see 10% of the galaxies in the universe. Kind of impressive, huh? All right. I will caution, however, that it's a theoretical study. It's not an observational study. Nobody has actually seen these galaxies, okay? So what questions does it bring up in an astrophysicist's mind? First of all, are the extrapolations to low mass robust? We have some good observations that go down to 10 to the 7th solar masses, okay? And they sort of disagree with some of these predictions, but they sort of agree. You find really good agreement up to like 10 to the 10th solar masses. But when you start going below that, you start getting a little bit of disagreement. And here they're extrapolating down to 10 to the 6th solar masses. So I'm not quite sure, as I read the paper, you know, is it really robust down to 10 to the 6th? You know, it's a very good paper, okay? I'm not trying to knock it. I'm just trying to give you ideas of what an astronomer thinks when they see things like this. And then my second question would have been, will JWST be able to see these galaxies? As you know, we've got the James Webb Space Telescope launching in 2018. We're going to be the scientific home of it here. We want to know, hey, if there are all these, if we're only seeing 10% of the galaxies in the universe, can JWST see those other 90%? The answer is, unfortunately, not. We're talking 10 to the 6th solar masses. We're just getting too small for JWST to see, okay? So we won't be able to verify this result with James Webb, okay? Which is, of course, one of the things that we would love to be able to do around here. But if this is true, all right, if this prediction is true, we'll figure out some way to figure out how to constrain it with the James Webb Space Telescope, or maybe even with later Hubble observations. And then finally, it brings up a question that's sort of a classic in my mind. What really qualifies as a galaxy, okay? Because we start talking about the early universe, and we're talking about the building blocks that will come together to form what we considered a real galaxy. Like this is a real galaxy, okay? It's a nice, big, large galaxy, all right? But if you take something that is 1/100,000th the size of this, okay, does that get to count as a full galaxy? All right, so when we're talking about these numbers of 100 billion versus 2 trillion galaxies, we're talking about the evolution of galaxies over time, the development of them from these small things to these big things, the mergers. You know, you may have a trillion galaxies early on simply because so many of them merge together to form a much smaller number later on, right? So you're getting into not just galaxies across space, but galaxies across time. It's a time-warped view of the universe that you have to think about. And do these small little objects, you know, there aren't what we would normally consider galaxies in the local universe. How much does it count? And so you get some very interesting questions. So this was a major press release for us this month, got a lot of attention, and I think it brings up some really great questions as to where we will want to look in cosmology for these very earliest galaxies in the universe. And it brings up an amazing prospect that, you know, hey, 90% of the galaxies out there still have yet to be discovered, which is always fun as an astronomer. All right, our second story tonight, the ghost of a star. We had a Halloween release last week, and I couldn't be happy with just this. I also called it a beautiful nebula. So we released this image on Thursday. Ooh, spooky. Let me tell you the story behind this image, okay? It's a single filter image that was colored green. Actually, it's a broadband image, waveband, so it does actually have a green tinge to it. But let me explain a little bit more about it, okay? So the story starts a little while ago, on July 4th, 1054. As you can read here, if you read ancient Chinese, the Chinese astronomers on July 4th, 1054, saw a guest star appear in the sky. I don't read Chinese, so this could be a recipe for mushu pork as far as I know, but I can look at the hieroglyphs in Shako Canyon, and here is the here's the crescent moon, and here is the guest star depicted there, about a hand's length away from the crescent moon on the sky, which also is believed to depict this guest star appearing in the sky 1,000 years ago. All right, if it was in the constellation Taurus, and when we look at the constellation Taurus today, we see that. The Crab Nebula, okay? What this was a supernova explosion. The explosion of a star becoming so bright that it could be seen during the daytime here on Earth, all right? And this star, the guts of it has blown across space at 10 million miles an hour for 1,000 years and created this gorgeous nebula. Now, this nebula is shown in 3 filters, hydrogen, nitrogen, and the broadband, a little bit of the broadband one that I talked. I think maybe it's hydrogen, nitrogen, oxygen, and a little bit of the broadband. And you can see all this filamentary stuff out here. Well, that's the narrowband filters that just pull out the individual elements. Okay? The ghost image that I showed you before, when I overlay it on top, is there. All right? So I'm going to blink back and forth. So here's the normal crab that we're used to, and there's the ghost. Normal, ghost. Normal. You can look right in here. You can see that stuff. That's not filled in the ghost. All right? So what we're seeing here with this this broadband image is that it is filling in much the sort of egg shape of all this filamentary structure sort of creates an egg shape, and the interior is filled in with this ghost image. All right? So here are the 2 images on the same scale, just separated so you can take a look at them. And you can see this blue image here roughly corresponds to the green that we released in the image on Friday. But there's even more cool stuff in this image. If we look straight in here in the interior, you can see there's something funky going on in there. Well, Hubble released an image of that previously. This is the central region. You see sort of ring structure here. Well, that comes out beautifully when you look in X-rays with the Chandra X-ray telescope. All right, you have a beautiful ring structure here, you have a bright dot in the center, and you have this material being spewed off. This is the dead star. This is the stellar remnant. It is a neutron star, a ball of neutrons about the size of the Baltimore Beltway, okay? Just all packed in, spinning 30 times a second. We know it's spinning 30 times a second because that neutron star has an immense magnetic field, all right, that creates pulses when that magnetic field sweeps across our line of view. 30 times a second, we get pulses from this, and hence we call it a pulsar. So the pulsar at the center of the Crab Nebula has this amazing magnetic field that's sweeping around 30 times a second, which of course is creating tremendous amounts of energy. So if you look at that in polarized light, and you're going to learn a lot about polarized light tonight, right, Toby? Yes. If you look at it in polarized light, you can actually see some of the pulsation, some of the effects of the magnetic field. This is a time-lapse series, okay? All right, and you can see material flowing away from that central neutron star. And it is a broadband image plus some polarized light in order to see the material flowing away, all right? And so in the Halloween spirit, since we're Baltimore and Edgar Allan Poe is related here, we call this the telltale heart, or the beating heart of the ghost of the Crab Nebula. So even though it's a dead star, it still has a beating heart. And that was our Halloween release for this year. All right. Now to our featured speaker. Our speaker tonight is Toby Marriage. He is from across the street at the Johns Hopkins University, where he is an assistant professor. He has been there for 7 years after having come to us from Princeton University. And he was kind of unusual that he was at Princeton for 14 years. He just couldn't graduate. No, he did his undergraduate work at Princeton, and then he did his graduate work at Princeton with a 1-year hiatus at Cambridge in England, right? Okay, so he had to get out of Princeton for just 1 year. But that's kind of unusual to be able to spend that long at one institution. And obviously, we are very fortunate to have him here in Baltimore. Ladies and gentlemen, Toby Marriage.
Great. So you can hear me okay? All right, cool. Good back there? All right, I'll assume so. Okay, great. Well, it's a real pleasure to be here tonight. This is a really excellent forum. I mean, I try to encourage my students to, learn for the joy of learning as opposed to for grades. And I think this is a good example of people learning for the joy of learning. Tonight I'm going to tell you about a project we have across the street at the Department of Physics and Astronomy at Johns Hopkins called the Cosmology Large Angular Scale Surveyor. And I'm going to keep the talk relatively short and with the hope that some of you will join me for a tour of our telescope building facility across the street. So I'm going to begin with the scientific goals of the Cosmology Large Angular Scale Surveyor, which from now on I'll refer to as CLASS. So with CLASS, we're trying to answer the primary question we're trying to answer is this: how did this happen? So that is, how did the universe happen? And in order to answer that, we need to essentially look back in time. We need to go back. We need to be able to probe the earliest moments of the universe to say, how did this all get started? And the tool we astronomers have for that is light, of course. So the light that we see on the sky is essentially a cosmic fossil record. And this comes from the fact that it takes light time to travel to us from distant objects. So if you consider, for instance, the sun, it takes light 8 minutes to reach us from the sun. So we're seeing the sun as it was 8 minutes ago. If, God forbid, the sun went out, we wouldn't know it for a pleasant 8 minutes. If you look further out, of course, you see stars. Those stars we're seeing as they were tens of years ago. And look further out, you get to nearby galaxies. Now you're looking back in the past a million years, or millions of years. Look even further out, you see the earlier galaxies in the universe. You're looking back billions of years. And if you look all the way back to before these galaxies formed, you see a wall of light, and that wall of light is called the cosmic microwave background. What's happened at this point is you've looked all the way back to the very earliest moments of the universe, some 13.7 billion years ago. And at that point, the universe was so dense that hydrogen, which makes up most of the gas or normal particles in the universe, was ionized. And you just see this opaque plasma of photons and electrons and protons zooming around. And so it just looks like a cosmic soup. And if you look very closely with a contrast of better than 1 in 100,000, you'll see bumps in the brightness and dark spots in this bright wall. And that is what we study with the cosmic microwave background. This is how it all began, and from this, all of this formed. So we have an answer. We can look back in time. We can use our time machine. Looking out is looking back, and we can say that these came from this. Or, to put it in pictures, this evolved from this. There's layers to everything, so of course the next question is, well, how did this happen? Unfortunately, you can't look past this wall in light. And so we have to infer from our physics what happened before this, what put this in place. And one of the best theories we have for how this got there is called inflation theory. And inflation theory posits that all of this structure in the very early universe grew from quantum fluctuations. These are subatomic fluctuations that quantum physics says have to be there. And the inflation theory posits that the early universe grew out of these random quantum fluctuations. I know, sounds crazy, but it explains a lot. In addition to the bumps in the early universe that grew into galaxies, inflation theory predicts that not only are there quantum fluctuations in this energy density that gives rise to gravitational wells into which pool our matter and into which grow our galaxies, there are also cosmic fluctuations in space-time itself. So space-time is rippling, stretching, squishing, squashing in the early universe. And these get blown up to cosmic scales as well. And these become universe-sized gravitational waves. So the squishing and squashing of space-time writ large across the entire universe. So speaking of squishing and squashing, so this is a picture of a gravitational wave. And what a gravitational wave does is it squashes space in one direction and it stretches it in the other. So this is a little animation. Let's see if it works. There we go. So squish, squash, squish, stretch, squash, etc. So as you can see, when it pulls in this direction, it pushes in that direction. And when it pushes in this direction, it pulls in that direction. So this is going to affect the light in the early universe. And in particular, what's going to happen is when you squish space like this, you basically boost the CMB, the cosmic microwave background, the light in the early universe. You boost the light in that direction. So you basically have, light beams traveling in like this in the middle of a gravitational wave. And what this does is it produces, what happens is these light beams come in and they scatter. They scatter off of that plasma in the early universe. And then they come to us polarized. So you may be familiar with the polarization of light from, say, if you're out fishing and sunlight comes off the water and is bright, and you can put on your polarized sunglasses and block the glare from the lake. But and this is exactly the same kind of thing. There's another analogy, again with sunlight, in the sky. So as sunlight passes through the atmosphere and it scatters, it actually ends up being polarized. So you're outside on a nice day, and especially as the sun's going down towards the horizon, you'll have a clear polarized pattern on the sky. In particular here, as is sort of schematically depicted, the polarization here of the light is mostly vertical, so the light oscillates in this direction. And out here, the scattered light oscillates in this direction, and out here, the light is relatively unpolarized. So if we apply a polarizing filter to this image, such that we block that vertical polarization, where we have vertically polarized light, it's going to go dark. And that's what you see. So if you walked outside with a polarized filter on your eyes at this time, you would actually see a dark band on the sky. So you can go out and experiment with this. The sky actually ends up being polarized in this way. And we're not the only ones that know about this. In fact, bees know about this. They actually use this to navigate. They have polarization-sensitive photoreceptors in their eyes, and they can use this polarization effect to tell the other bees where to get pollen. They can tell east from north from west, using the fact that the sky is polarized here towards the north and not towards the east. So again, the point here is that when you get scattering of light, you get this polarization. Okay, so just to reemphasize, so in an analogy with scattered sunlight, the CMB is scattered through polarization due to this gravitational wave enhancement. Good news for bees in the early universe. Nah, there weren't any bees in the early universe. Okay. All right, so, but the point here is that gravitational waves produce this polarization in the CMB, and we can go out and look for that in order to find evidence for these gravitational waves. So to completely stretch my analogy to its breaking strength, the bees use the polarization of the sun to find pollen. We use the polarization of the CMB to find the primordial gravitational waves from inflation. All right. So here we go. So how do we do that? We don't have photoreceptors that are polarization sensitive in our eyes to see the CMB. We have to build telescopes. And so that's what we're doing. So this is class. So this is an artist's rendition of class. It's an array of 4 telescopes. What you're looking at here are 2 structures, 2 pedestals, and on each pedestal there are 2 telescopes with beams looking at the sky through beams represented by these four green columns. And in particular, these telescopes operate at 4 different wavelengths or 4 different frequencies, going from here at about a millimeter wavelength. So these are very long frequencies compared to, say, optical light, which is sub-micron. So we're looking at millimeter wavelengths. So this is this telescope here looks at a millimeter and 2 millimeter light. These 2 telescopes look at light that's about 3 millimeters long in wavelength. And this telescope looks at an even longer wavelength in the sort of 6 to 7 millimeter range. So 4 telescopes, 4 frequencies in the middle of the Atacama Desert of northern Chile at 5,200 meters. And we'll have more on that on the site in a little bit. But let's dig in a little bit to the design of the telescope. So one first question is, why 4 frequencies, right? And, it's all about fruit. But it's a good analogy. So basically, these frequencies in the microwave, the frequencies we're looking at, correspond to colors. Now, if you're looking at the sky or any other picture without color, if you're looking at stuff that looks similar, say an orange, a lime, and a lemon, or is it a lime and an orange? Well, I can't tell because there's not color. But yeah, so the point here is that without colors, it's hard to tell things apart, both on the sky and in real life. So you add colors, and you can tell your oranges from your lemons. Or in our game, you can tell the cosmic microwave background from other sources of microwave radiation. Mainly from our galaxy, you're talking about emission from warm dust, and or emission from like the emission you saw from the Crab Nebula from accelerated electrons. In any case, you want to be able to, you basically, what we, just like you need red, blue, and green in this picture to tell these fruit apart, we need 40 gigahertz, 90 gigahertz, 150 gigahertz, and 220 gigahertz in order to tell the dust apart from the cosmic microwave background. So that's why we have the 4 frequencies, is basically to make a color picture of the sky, to know that what we're looking at is actually this polarization signature from primordial gravitational waves. All right, so let's look under the hood. So this is one of the telescopes, and all the telescopes look similar, but operate at these different frequencies. So let's follow the light. So the light enters the telescope here. And the light comes in and it reflects off of this thing that I've got labeled here as the VPM. This stands for Variable Delay Polarization Modulator. And let's just leave that for now. I'm going to talk a lot about that later, because this is really what makes class special. But let's just let the light reflect off of that now. It bounces off of it reflects off these mirrors, primary, secondary, and the light travels into this what we call a cryogenic receiver, which in the sense that it receives the light. Cryogenic in the sense that it's cold. And it goes through these cryogenic lenses. This lens sits at 4 Kelvin, so 4 degrees above absolute zero. This lens sits at 1 Kelvin, and it finally reaches our detectors that sit in the focal plane of the telescope. And these are only 1/10 of a Kelvin above absolute zero. We need them to be that cold because the signal that we're looking at is exceptionally faint. And if we have thermal fluctuations that are, say, the level of thermal fluctuations in this room, then the noise from those thermal fluctuations completely swamp our signal. So that's why we need to cool our detectors to so cold. Zooming into the detectors, here they are. These are actually microfabricated detectors that are made just down the street at NASA Goddard Space Flight Center, and we collaborate with the scientists there to build these detectors. All right, so I promised I'd talk about this VPM, or this Variable Delay Polarization Modulator. So the VPM, as it's shown here, it's about 60 centimeters across. And what you're looking at here, you can sort of see a haze in front of the circular mirror. That haze is about a few kilometers worth of 100 micron wire stretched to its breaking strength and separated by about as much space. So you have a few kilometers of wire stretched in this 60 centimeter aperture and supported by this frame at a few tons of force. And so the idea here is that this wire grid reflects one polarization because the grid's in one direction and transmits another to this mirror. And that's the VPM deployed in the field with its creator, Katie. She's a graduate student over in our labs. But she spent about 3 months up in the desert, and this was a good moment for her. So to say what's going on with this polarization modulator a little bit more schematically, here's that wire grid, that kilometer worth of wires stretched in a comb like this. And we have the mirror right up against the wires. And what we're going to do is we're going to move that mirror. And this is what the VPM does. It has a very tense wire grid in front, and it has a mirror that sits behind it and moves back and forth. And so what you can see is happening here is that one polarization state, the polarization state that's like this, is transmitting through the wire grid, going to the mirror, and the other polarization state is reflecting off the grid. And so in this way, we separate in phase one polarization state from the other. And we move this mirror at about 10 hertz, so up and down 10 times a second. And in this way, we modulate this polarization signal. So the picture is this. We have this signal coming in from the CMB, and we run it through this variable delay polarization modulator, and we move that mirror up and down. And so the signal gets encoded at this 10 hertz frequency, at this high frequency. And then you have this noise from the telescope and from, say, the atmosphere on which this frequency rides. So this is a little bit like your car radios. You can tune into a station and hear a signal. You tune a little bit to the right from that station, all you hear is fuzz. And so this is what we're doing. We're basically using this variable delay polarization modulator, we're putting our cosmic microwave background signal at a specific frequency that's away from our noise. So I've designed we've created a little audio demonstration of this, which will sort of demonstrate how this technique works. So the cosmic microwave background polarization is going to be represented by a voice here, and we're going to show how that can get drowned out. But then when you move it to a higher frequency, you'll be able to hear it despite the noise. So let's see how this goes. So here's the signal.
The cosmic microwave background polarization.
Okay, and here's the noise. This is like the low frequency noise in our telescope. Now we put them together, and it's going to be hard to hear the signal.
The cosmic microwave background polarization.
Hard to hear the signal. Now we're going to boost the signal at a higher frequency.
The cosmic microwave background polarization.
Okay, now we're going to add the noise.
The cosmic microwave background polarization.
That's exactly how class works. So we take this signal that would otherwise be, a low frequency like my voice, and drowned in this low frequency noise, and we boost it to this higher frequency using that BPM, and then we can disentangle that from the noise, just like your ear could disentangle the higher frequency signal from the low frequency noise. This is a very good analogy. Okay, so we build this thing, and then what do? So the first step is, we bring this all together. We put the VPM on the telescope over in the physics department. That's step one. Step two, we tear it down and put it into shipping containers, and then we put it on a boat in Baltimore Harbor, and that boat goes down, goes through the Panama Canal, and to a port in northern Chile, and then put it on trucks, and then we truck it up to the site at 5,200 meters here and install it. So, and to zoom into the site, so here's our site. So this is basically completely isolated. We have to have our own generators, have our fuel delivered. This was installed by, postdocs, graduate students, and the occasional professor. We contracted a company to put in these slabs and put in some conduit, but it was the students pulling the power cables through these conduit and connecting these telescopes. So this is the first telescope, that 40 gigahertz telescope in the desert. And you can see what we've done is we've retrofitted some of these shipping containers to be our control room, our machine shop, our laboratory, etc. And Again, we're very excited back in May to get our first light. This is when the telescope first sees something. In our case, it was the moon, which, you know, we confirmed it was there. It's good. But we were mainly excited to see the detectors light up, of course, and we've been making cosmological observations since. And one thing I really want to emphasize here is that it really is a student and young scientist training ground. These guys do so much, and you know, they really are the engine for this project. And a lot of these folks are over here across the street. And so I wanted to leave you with a little bit of a, so I said a few things about the site, but I wanted to play something for you that we made this summer that gives you an even better idea of our operations out there. So this is about a couple minute video, and then we'll wrap up. Welcome to the class low altitude headquarters in San Pedro de Atacama, Chile, at 2,400 meters or 8,000 feet. This is where the class team eats and sleeps. Above me, you can see the radio link that the class team uses to talk to the mountain site. They use this link to beam down data and also to control the telescopes. San Pedro de Atacama, Chile, is a rural oasis town in the middle of the Atacama Desert. It has striking geological features, such as that which you see behind me. This is the landscape on the drive up to the class site. This is Cerro Toco. This is the mountain on which class is sited.
Cerro Toco is an extinct volcano. There used to be a sulfur mine on Cerro Toco, but now it's dedicated to observations of the cosmic microwave background, or CMB. Welcome to the class high altitude mountain site at 5,200 meters. This is the first of 4 class telescopes, which was installed in the spring of 2016. This telescope scans the sky, as you can see here. As the telescope scans, the light from the CMB enters the cone at the top of the telescope, reflects off of mirrors, and is focused onto cryogenic detectors operating at near absolute zero temperature. This telescope scans the sky night and day in order to make a map. We search this map for the faint signal in the polarization of the cosmic microwave background from gravitational radiation in the early universe, which can tell us how the universe began. From this perspective, you can see the entire class site. To my right is the telescope scanning the CMB. You can see into the cone at the top of the telescope into which the light enters. To the right of the telescope, you see our control room, our laboratory container, and our machine shop container where we put together the telescope. So this is Denise Vaya and Manwei Chan. They're the engineers that operate the class telescope. They're here year-round. Denise just graduated from the Federal University of Ouro Preto in Brazil, and Manwei just graduated from Johns Hopkins University.
Denise, how are the cryogenic temperatures?
Good, 30 millikelvin. What are the colors reading?
30 degrees.
All right, another good day at the site. Let's go down the mountain.
Yeah, sounds good.
All right. So this is just starting. We just moved that first telescope out. We got another 3 telescopes to deploy over the next couple of years. The survey goes for 5 years. So you can follow us at this address and stay tuned. Thank you.
telescopes be surrounding those laboratory and machine shop and other trailers that you have, or will they be located distance away?
No, it's a pretty compact site. So it's within that fenced area. So the second telescope actually goes on the same pedestal as the one you saw there, and we'll be shipping out the other pedestal next year. Well, this looked like Nova, didn't it? No, we've enjoyed some work with the Sun and other media outlets, but not Nova yet. We're working on it. Yeah. There's a lot of great stuff going on. So. Yeah. Okay. So that may have been right next door. It's the most expensive ground-based telescope in the world. It's called the Atacama Large Millimeter Array, or ALMA, and it's 60 dishes, not 4. And they do wonderful stuff all the way from study high redshift galaxies to look for the disks out of which planets form. So there's a lot going on out there. So I said the site is isolated, and it is quite isolated, but we do have other astronomical facilities. Yeah.
There are different frequencies in each telescope. Will you point them all at the same place to distinguish more?
Exactly.
Okay, Toby, we need to, I always forget, we need to repeat the question so the folks on the website, webcast can hear the questions.
Okay, sounds good. So that's great. So the question is, given the 4 frequencies, will we be pointing the telescope at the same sky in order to make this color image, basically, of the early universe? And absolutely, we'll be doing that. But it's helped by the fact that we're mapping 70% of the sky. So it's hard not to point at the sky that we're looking at. And we don't have to point at exactly the same time. So basically, the universe isn't going anywhere. So just like if you had a family standing for a portrait, you could come by and take RGB pictures of them and subsequent times and put them together. That's sort of what we're doing. We're imaging the universe with the different frequencies, the same part of the universe, and putting them together. But we don't necessarily have to have them pointed simultaneously at the same spot. In the back.
I was wondering, are there any other species on planet Earth that can see in polarized light?
That's a great question. Yeah, absolutely. There are other. So the question is, thanks. Are there other? I'm going to learn.
I have to learn myself. I have to remember every month.
Are there other species on planet Earth which can see this polarization with their eyes? And yeah, it turns out to be sort of other insects. For some reason, this seems to be the particular domain of these animals, these creatures. Although I learned about this through this magical place called Wikipedia, and so you can read about it there too. I think there's probably more. Yeah, go for it.
Yes, on your signal enhancement process that you demonstrated, you had an intended signal, your voice in this case, and you played the noise environment. Separate from that, you combined the two, you couldn't hear the intended signal, but then you translated the desired signal, your voice, to a higher frequency. Is there something about the spectral density of that noise process, in a particular band, whether it was 40 gigahertz or 90 gigahertz, that allowed you to move that signal to a higher frequency as you described and subsequently get that higher signal more efficiently?
Sure. So the question is going back to the point about modulation, and correctly describing how in the example of the voice, which was a signal, was brought to higher frequency, such that you could hear it despite the low the low frequency noise in which it was otherwise drowned out. And then the question is there a particular aspect of our signal, say at 40 gigahertz, that makes it possible to modulate it up?
Well, I was asking about the noise spectrum.
Oh, the noise spectral density. Yeah.
Is it somehow nonlinear, or is there some characteristic?
Sure, yeah. So the noise that we get in our telescope, you can classify noise by colors. So the noise that we see in our telescope is usually can be referred to as brown noise. So this is noise that is higher at lower frequencies, and lower at higher frequencies, and essentially what happens here is it's important to just essentially what we're doing with the telescope is we're moving basically we're observing the sky and looking at the CMB polarization, and it's coming in at 40 gigahertz, right? But what we're doing is we're just like, you know, when you see blue light, you don't see, you know, the electromagnetic signal from that blue light going up and down. You just see some blue intensity. So we're just imaging the intensity or the polarization magnitude of the light at 40 gigahertz. And then what we're doing is taking that signal and we're putting it at just 10 hertz. So something quite manageable. And the point here is that if you take the way you saw the telescope scanning on the sky, and the atmosphere is blowing by, so that atmosphere is a significant source of noise. It has structure in it, and it's bright and dark, and as it blows across, what happens is that we see that in the telescope, the brightness of the atmosphere, and it's much brighter than the CMB. And basically the spectrum of that signal or the noise, if you will, of that atmosphere has this brown noise spectrum. And so we modulate up above that. It basically goes away by about a hertz. So we get to 10 hertz above that noise. Actually, a really cool thing to do is, again, it goes back to Wikipedia. If you look up the color of noise, this is actually what gave me the idea for this demo, is on Wikipedia you have, they actually have the sound of different noise. So there's, you've probably heard of white noise. So the brown noise sort of sounded like the ocean. But white noise, you know, it sounds like your
Doesn't
radio.
HBO use white noise in one of their promo?
Yeah, exactly, yeah. So, but you can hear there's pink noise, there's red noise, there's all kinds of noise, gray noise.
What color is your noise?
Yeah, that's right. So you can go find your color.
More questions.
In the diagram, you implied that your detectors are operating at 4 degrees Kelvin. How do you maintain that low temperature continually in the field?
That's a great question. So, so
repeat the question.
Oh, sorry.
No.
So the question is, how do we maintain the cold temperatures of our telescope, 4 Kelvin, all the way down to a fraction of a Kelvin in the field, basically, it's not too different from your refrigerator at home, except for really souped up. You have a really high electric bill if you had our refrigerators. And we use helium. So we compress helium and then we expand helium. And when you expand the gas, it cools, right? And so that's basically how we get down to 4 Kelvin. It's a closed cycle, just like the fridge. Where the material comes in, you expand it, and it cools down, and then you basically use that cold material to cool your food. In this case, we're cooling our cryogenic detectors, and then that gets us to 4 Kelvin, and then we want to get even colder. We want to get to a fraction of a Kelvin, and we use another closed system. But now we use, which still uses helium. But it uses an exotic isotope of helium, helium-3. So it uses a mixture of regular helium, helium-4 and helium-3. And it's essentially evaporating helium-3 through a mixture of, through a helium-3 deprived mixture of helium-3 and 4. And so it's fancy kind of evaporative cooling that gets us down to the coldest temperatures, a little bit like the evaporative cooling on your skin, but more so.
When you're getting to these very low temperatures, the materials that you're dealing with can have peculiar properties.
Absolutely, yeah. For instance, our detectors are superconductors, so we actually operate our detectors right at the transition between being a normal metal and a metal without any resistance. So we use a lot of fancy tricks in there. We use quantum interference to read out our detectors. It just gets cooler. I could go on.
What is the resolution of the telescope?
That's a great question. Okay, so the question is, what is the resolution of the telescope? So this signal, like I said, we're going for these universe-sized gravitational waves, and even if you put these waves at a very far distance, as far out as we're looking at, they're still really big. So our telescopes are essentially have degree scale resolution. So you saw the moon right at the beginning, comparing to Hubble Deep Field. Our beams are twice that big. So it's our resolution would. The moon looks like a point to us.
Okay, so let me just put that into perspective. Hubble's resolution is a 20th of an arc second, and an arc second is 1/3,600th of a degree. So that makes about what? 70,000. His resolution is 70,000. Hubble's resolution is 70,000 times better than his resolution. Okay, but Hubble is looking at really tiny things in the sky. He's looking at really big things in the sky. Okay.
Different tool, different job.
Exactly.
So you sort of regard that as almost a light meter as opposed to what you more think of telescope.
Yeah. I mean, I think there's so many bells and whistles with this thing that it's almost more like an apparatus. Yeah, but it is a telescope.
There's what 40,000 square degrees in the sky, so he's still got a good number of pixels to look at.
No, we're definitely still doing what one would conventionally call imaging, but like in the 40 gigahertz receiver, we only have what would be called 32 pixels in our camera. So it's a different game, but it's analogous. Yeah.
Do you have any plan to use new glass cameras to cover the whole sky? Cover the southern sky?
That's a great question. So the question is, are we going to build more cameras in order to get to the whole sky? And from the Atacama Desert there, so that's in the tropics, if you can believe it. Actually, most of the deserts in the world are, surprisingly. In any case, it's a subtropic. But in any case, the point is, it's not far from the equator. So from that location, we can actually image most of the sky. But yeah, there are thinking more than 5 years out. A northern hemispheric site. There are reasonably good sites in the northern hemisphere that are being explored. The two main places people look for the CMB are here in the Atacama Desert, and the other one is the South Pole. So exotic spots. Everything. So the question is, and actually, that's Chantal. She was she's helped make this early. She was there at the beginning. So the question is, what's been the most challenging? What's been the most challenging part of class? And I think I think for a lot of us, I mean, most of us, I mean, are pretty young. I mean, in the context in class, and I think probably the biggest challenge is just realizing we could do it. and just sort of overcoming this sort of perception of like, oh, this is a huge project, and sort of now we got it in the field. So this is
but related
really
to that, I mean, when starting the James Webb Space Telescope, they had several new technologies they had to invent while building the new telescope.
Sure.
And you're talking about using quantum interference to read out your detectors,
right?
And working with the liquid helium, the helium cooling and tritium cooling and such. How much of that was already known versus how much did you have any major technologies you had to invent to try and get something like this working? Yeah,
those detectors that are made at NASA Goddard, we've been working with them to develop them over the last 6 years. They're unique in the field of CMB observation. So that's required a lot of development. For instance, that 40 gigahertz telescope and the array of detectors that's the first ever camera like that.
Right.
Those VPMs you saw that Katie built, those have never been built before. So it's or used in this way.
Well, I find that the public likes to hear about what's the highlight the real R&D aspect of science. I mean, sometimes people think that we'll just build another telescope and it's just the same old telescope. But really, there's so many of these science experiments that are pushing the edge boundaries of science, but they're also pushing the boundaries of technology. In order to enable new science. And
I mean, there's basically three main parts to class. One is the first one is, of course, the science that we're going after, and then the second one is training scientists, and then the third is this technology development. So absolutely. Yeah.
Who is funding you?
Okay, the question is who is funding us? So why you, of course.
Specifically you, only your tax dollar.
No, I mean, of course, that's the truth, right? So we're primarily funded through the National Science Foundation, and they've supported both the development of the instrument, and now they've just recently funded us to execute the 5-year survey. We also have help from a lot of other sources. The detector development is, like I said, is done at NASA. So NASA supports the technology development of those detectors, looking ahead towards a space mission to do this type of thing. And we also have private contributions through folks who are just excited about the telescope.
And the amount? The amount?
The total amount, the sum. It's in the $20 million ballpark.
How long will the project take?
So this, what I'm showing you here is sort of roughly 7 years in the making from sort of serious building. And then it's going to be another 5 years to the science. So these projects end up being on this sort of medium scale project is on the sort of 10-year time scale.
At this stage of the game, do you have indication that you're on the right track?
The question is, are we on the right track? And yes, we're still, the data is just coming in, and I can't say much about it until we fully tease things out. But yes, things are looking good.
Do you use enormous amounts of electricity to keep the telescope cool? And when you have 4 telescopes up there, is that a challenge to get the electricity up there?
The question is, how much power does it take to run these telescopes? So the generators that were in the site picture, those are sort of derated for. So we're at 17,000 feet. It's half an atmosphere. So those generators are about 200 kilowatt generators, and you derate them by roughly half, and that's roughly the power consumption of the full observatory. So each one of for each one of those helium refrigerators takes about 10 kilowatts, and then you've got to move the telescopes. You got to keep people from freezing when they're at the site. Run heaters. We have oxygen. We have oxygen concentrators for folks to be smarter at the site, and those each take 4 kilowatts, and you have to. Yeah, or not that much. In any case, yeah, a lot of power.
Okay, yeah, just a couple more because you want to take people across the street.
Yeah, that'd be great.
Hang too late. So here.
At this point in your research, can you foresee any practical implication or applications for this in the real world?
Oh yeah, okay. I mean, I think there's two different aspects, right? There's the science aspect, and that one's just looking way out, right? So that's how does understanding how the universe was created, how is that going to enable us to advance humanity? And we don't know that yet, but certainly would be good to know to make progress. So that's the big that's the one side, and then the other side is this technology development. Like, for instance, these cold detectors that are so sensitive to find faint ripples of polarization in the early universe can be used for remote sensing and other applications. You can use them in different wave bands, look for radiation, this type of thing. So that's one example. Polarization modulation. Polarization's everywhere. If bees got a hold of that modulator, but we have honey all over the place.
We'd have super bees
that's
controlling the universe.
Yeah, but but seriously, the benefits of the research are through this sort of big picture science. Where is that going to take us? You have to think far out, and but the technology to transfer.
Okay. Peter, I have to cut you off because there was a gentleman in the back there and this gentleman over there. I have to then last two questions.
Sure. I'm just wondering about the spectral selectivity of the telescope. Where does that come from? Is that built into the detector, or do the 4K, 1K lenses have some?
Sure. Yeah. So the question is, where does the spectral selectivity of the telescope come in? And it's actually built right onto those chips. What happens is the light comes into the detector from the telescope, focuses the light onto the detector, and the detector actually picks up the electromagnetic waves and sends it through circuitry, so microwave circuitry, so high-speed electronic circuitry, and we actually implement filters on the silicon there to define the bands. There are other places where we can choke down and limit long wavelengths and things like that. And we play a lot of games to make sure that we don't see that pesky high frequency short wavelength light doesn't get in. And that's one of the innovations with this detector. So there's a bunch of different ways which we sort of select out our specific band so we don't look at something we don't want to see.
Okay, and you have the last question.
You said at the beginning that information about the cosmic microwave background will help us understand how the universe was formed or how it was created. I don't know if you said how it would help us understand that. If you said that, and went over my head, I apologize.
No, I probably just said it. No, okay. So the question is, in what way does the CMB help us understand the early universe? Or okay, great. No, that's a great question to end on. So basically, this is a snapshot of the early universe. So the first answer is simply it is the early universe. So in the same way as Hubble can image, what the galaxies look like, 11 billion years ago or whatever, we're saying what does the universe look like when it was 13.7 billion years old it's basically a thermal soup. It's like looking into a kiln, and it's hot. And so that's what we're seeing. We're imaging that heat from the early universe. So that's sort of the basic level. And then what the really awesome thing about the early universe is it's a lot simpler than the late universe. So you look around and you see all these different types of galaxies, red, blue, some of them with jets shooting out of them, stuff like that. This is hard to understand. This has very complicated these things have very complicated physics and very complicated histories. The early universe it does not have a long history, and because it's just this soup, right? Our physics actually describe it pretty well. So what we can do is we can take that picture and use pretty basic physics, modern physics, but not too much more than electromagnetism, thermodynamics. Throw in some nuclear physics, but some stuff we know pretty well and we've constrained from the laboratory. And you can take that picture and you can go backwards and you can go forwards with it. And so the basic answer is that physics of the early universe is actually relatively it's sort of fundamental in some sense that our laws can and simple in the way that our law in the sense that it's not. Doesn't have all this complexity like these life forms in this room. They're so complex we can't describe them. But we can describe the early universe with our laws.
Okay. So give me a hand. Thanks. All right. Toby's going to pack up his stuff, and then he'll be able to take whoever wants to go across the street. Next month, we have Christine Chen talking about debris disks, and you won't want to miss it, but I will miss it because I will be in San Francisco next month giving a talk at the Morrison Planetarium the night before this, so I won't be back in time. So I'll have a great Thanksgiving. I'll have a great holiday season. I won't see you till 2017, but I'll have a guest host here to help Christine Chen give you an amazing talk next month. Thank you all for coming, and we'll see you next time. Activity where middle schoolers count all the galaxies in the Hubble Ultra Deep Field. How do we do it? Well, we divide it into 100 smaller squares, okay? And then we have the middle schoolers look at these individual squares and then count the galaxies in them, okay? They usually come up with like 50 or 70 galaxies in these. And then if there are 100 squares and there's, say, 50 galaxies in each, how many are there total? 50 times 100? 5,000, okay? So they tend to get 5,000, 10,000 galaxies or so in this. And well, 5,000 to 7,000 is what the middle schoolers usually estimate. When you do it really carefully by astronomers, they count about 10,000 galaxies in this image. Now, this is a really tiny image. So if there are 10,000 galaxies in this image, how many are there in the entire universe? Well, to do that, you then have to know how big this is on the sky. And so we walk the middle schoolers through that part as well, and we say that, okay, well, here is the size of that ultra-deep field compared to the full moon, the size of the full moon on the sky. All right? And it's, it's a small part of the full moon, and the full moon itself is also a small part of the sky. And if you do the mathematics, all right, the size of the Hubble Deep Field compared to an entire sphere, the number is, across the entire sky, there are 12,746,784 patches the same size as the Hubble Ultra Deep Field. Okay? So, 10,000 galaxies in the Hubble Ultra Deep Field, 12 million ultra deep fields across the sky. If it's representative, then we get about 120 billion galaxies across the entire sky. So, using that, hey Thomas, are we all ready? He gives us the thumbs up. All right, let's begin. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. It is my pleasure to be your host tonight. I am Dr. Frank Summers of the Space Telescope Science Institute, Office of Public Outreach. When you came in, I'm sorry I didn't put any pictures over this side. Over that side, there's a plenty of pictures. Tonight's pictures are not the same. There's a whole jumble of pictures. We have a bunch of OPPO staff moving offices, and when they move their offices, they say, where did these come from? And then they go, here, Frank, give these away at the public lecture series. So tonight you have a whole bunch of cool images and random lithographs that have come out of people's offices. If you didn't get one on the way in, please pick one on the way out. What do I have here? It looks like this is a wonderful edge-on galaxy, NGC 5866. All right, if you want 5866, hurry down here afterwards. It'll be right here. All right. Tonight's talk will be the Cosmology Large Angular Scale Surveyor, which in the tradition of physics and astronomy has a nice acronym of CLASS, okay? So you're going to get a classy talk tonight, okay? Really classy. All right, and next month we have Christine Chen talking about debris disks and the evolution of planetary systems. January, I don't have a speaker for January. It's difficult to rope somebody in for January. I will work very hard at it over the next month and announce that. So right now we still have our infamous TBA. And in February we have a very special talk, ultra deep field, which I said we observed over a decade ago. To the depth of the ultra deep field, there are roughly 100 billion galaxies in the universe, okay? And that has been sort of our standard number for the number of galaxies in the universe for over a decade. But what about the galaxies that Hubble doesn't see? Because notice, this says to the depth of the Hubble ultra deep field. There are things that Hubble doesn't see, right? They could be too faint for Hubble to see them, or they could be too small for Hubble to see them, or they could radiate in infrared or other wavelengths that Hubble doesn't see, right? So we recently had a paper called The Evolution of the Galaxy Number Density at Z less than 8 and Its Implications, which may not make much sense to you, but the idea is to try and account for all the galaxies that we don't see in the Hubble Ultra Deep Field. So here is the study. And I'm going to read this verbatim because there's a lot to it, and I'll think. How many galaxies are potentially detectable within the universe if deep imaging over all wavelengths could be carried out in every location of the sky without any interference from the galaxy or other contamination? So that covers all the things that I just said. The entire sky in all wavelengths without any of this foreground contamination or stuff blocking, right? Which you could see every single galaxy out there. That's what this study is trying to do, okay? What is a galaxy for them? They say, well, they consider galaxies down to 1 million solar masses. Our Milky Way galaxy total mass is about 10 to the 12th. Priyamvada Nayarajan from Yale is coming down, and she will be giving a talk on her book, Mapping the Heavens, okay? So it's rare that I get because I have no travel budget for this lecture series, okay? So when I can get somebody in from outside, I'm really happy to be able to bring you somebody who's not from Space Telescope or Hopkins. Nothing against the Hopkins and Space Telescope people, because we are wonderful folks. But being able to bring you somebody from another university is also pleasant. Okay, I'll talk about construction. Since you're here, you know about the construction. But for the people watching this on the web, if you come to visit us, the road north of us is closed. So you can see the map here. This red stuff up here is closed. If you try to come in here, you won't be able to. You have to come all the way around here and then back up to get to us. All right. If you want to know more about this here, the website is here. There's the website on the San Martin project. This will probably last through next month and will not be there in January, we hope. We don't know. We'll let you know next month what the condition is, okay? All right. Let's see, our website, if you just search for Hubble Public Talks, you should find this. It has our list of our upcoming lectures. It has links to our online YouTube and webcasting, and as well as the archives, our playlists on YouTube and our archive from our wonderful webcasting folks. There are 10 years of these wonderful public lectures there for you to peruse. All right, you can also sign up for our email list, which will be helpful in December when we send out the email saying, yes, it's open, no, it's not open, for the construction update, okay? We can also, these announcements can also be signed up at maillist.stsci.edu if you should so desire. It's just much easier from our website. If you would like to send us mail and have us a comment or question, it's publiclecture@stsci.edu. We're also on social media, Facebook, Twitter, Google+, Pinterest. I'm on Facebook and Google+ and Twitter, and I have a blog on Hubble site if you want to follow some of the things I like to talk about. All right? There will be no observatory tonight. One, it's cloudy, and two, we have a special treat for you tonight. Our speaker has invited you across the street to look at the observatory that he's building, the facility for the Cosmology Large Angular Scale Surveyor. So at the end of the lecture, if you would like to go across the street to the facility, hang around, and after Toby's finished answering his questions and put away his laptop, we'll take you across the street for that, okay? All right. Now, our news from the universe for November 2016. Our top story tonight: make the universe great again. You knew I couldn't get through this without one election pun in this, right? Okay, so what am I talking about? Well, let's start back in 2004 with the Hubble Ultra Deep Field. Now, this is a picture of lots and lots of galaxies. How many galaxies? Well, some of you may know, but actually we do a educational